All right. Good evening once again, everyone. And happy new month to everyone here. We've come a long way. This is going to be the last month of this program. We started July, August, then we just entered September. So this is going to be our project month as well, right? We are actually already rounding up with what we have to look at. Yeah, and also apologies for starting late. I know we already prepped our minds to start by 5 p.m. and I really want to apologize for the delay. All right, so I hope we are able to round off and um, finish up what we have today on time. So I actually we are going to do that under 2 hours. Hopefully, if we can do that under in 1 hour 30 minutes, it's going to actually be perfect. But let's just see. So we're going straight into what we have for today. So yesterday we looked at other machine learning algorithms. We looked at KNN, k-nearest neighbors. We looked at SVM, and we also looked at decision trees. So that is what we've been doing so far. We've actually looked at a couple of these machine learning algorithms. Previously, we looked at linear regression and logistic regression. And trust me, there are a whole lot of them, but these ones that we're looking at are the most common one. They're the ones that you'll be using mostly when building machine learning models. So you need to get familiar with them. Okay. So yeah, today we'll continue from where we stopped. We are going to look at what we call ensemble learning technique. Okay, we're going to be looking at that. So we have some ML algorithms that use ensemble learning techniques to in building and creating ML models. So we'll look at examples and how we can go about them. The materials for yesterday have already been posted, so you would have the video already on YouTube. On the explanation sheet, I actually thought I posted it yesterday. The class of just reminded me this afternoon, so I had to go and check, and I actually was about uploading it, but I didn't finish the upload. So it's up already in the Google Classroom. You probably have seen it by now. So I'm still waiting for those that had issues with their week 7 assignment, right? So I asked those that were affected that didn't get their score to put out their name on a list. I've not gotten enough names that corresponds to the number of persons that had those issues. So once I get this list and I resolve the issue, I will not attend to anything regarding the week 7 assignment. So that's why I'm still taking time, all right, and waiting for other persons to put down their names. So that's just going to be the announcements, and we are going immediately. We are going to immediately start with what we have today. So just give me a sec. Let me share my screen. All right. So please, can everyone confirm if you can see my screen? Can everyone confirm if you can see my screen? All right. Okay. All right, that's fine. The material for this class is yet to be posted, so I'm going to just do that after this class here. All right, all right. So as you can see on the screen, we'll be looking at ensemble learning. All right, ensemble learning. Ensemble learning is a technique in machine learning that is very, very important. So today we'll look at what it means and the different things you need to know concerning ensemble learning. So as you can see, these are the outlines. We'll look at what ensemble learning is, look at ensemble learning techniques, we'll look at bagging, we'll look at example of bagging algorithm, which is random forest, we'll look at boosting and examples of boosting as well. So this PCA shouldn't be here. This is going to be in the next class. All right, so these are the things we're going to be looking at today. And trust me, you don't, it's not going to be difficult to understand. All right. This one is actually easier to grasp since you already have the foundation and of machine learning and some other things that we've looked at already. So let's just, without further ado, let's just move straight to it. So what exactly is ensemble learning? So before now, I believe some of us should know what ensemble is. Ensemble is a generic word that is not really specific to any field. It is not specific to machine learning. It's a normal English word that actually mean a collection of things. When you say ensemble of something, it basically mean a collection of different things to make one particular thing. All right. So it's like collection of different parts to make a whole, or collection of different. So that is what ensemble is. If you already know what it means, that's fine. It's going to help you understand this better, right? So ensemble is basically a collection of several items, all right, into one, to make up one particular item. So you refer to them, those items that you've collected, as an ensemble. Okay, so let's look at how it applies to machine learning. So in machine learning, ensemble learning refers to a machine learning approach. So it's actually an approach. Ensemble learning is not an algorithm. I need you to take note of that. Ensemble learning is an approach. Okay, is a technique. Under ensemble learning, you will now see different kinds of machine learning algorithms that we're going to be looking at. So I need you to start making those differences in your head now, so you don't confuse yourself. Ensemble learning is not an ML algorithm. It's not a machine learning algorithm. It's a technique and approach, all right, that is used in machine learning. So as you can see here, ensemble learning refers to a machine learning approach where several models, all right, remember what I told you about ensemble. Several models are trained to address a common what problem. So that is basically what it is. Ensemble learning refers to a machine learning approach where several models are trained to address a common what problem. Now, we'll be looking at machine learning algorithm. We'll be looking at linear regression, logistic regression, KNN, and the likes. All right. So we've looked at how we can use each of these ML algorithm to create or to train a machine learning model and make prediction. That's the standard. That's the traditional way. That is the one you are familiar with. Okay. So coming to ensemble learning now. Ensemble learning, you are now actually not depending on just one model. You are creating several different models for one task. All right, you are actually creating several models for one task. It's like, for example, now you have you want to like go to the market and you need ideas. Like, let's say you want to go shopping for clothes, and you are not really conversant with how clothes are being sold in the market, or the style to choose and all of that. So you need something to help you make decisions. So you need someone. So you went to a friend of yours that is actually an expert, or the person is conversant with the clothing market. You now ask that your friend, okay, see, this is what I want to do. What do you think I should do? Give me advice. That is equivalent to relying on just one ML model. You are relying on just one person to give you to help you with a particular problem or task. All right, that is what you've learned before. This is just an analogy to using one ML model to solve a particular task. So when it comes to ensemble learning, now you are not just relying on one particular person. You're not relying on that your single friend. You are now calling, let's say, like 5 of your friends or 10 of your friends. you will now ask each of them, okay, what style do you think I should get for this particular occasion, or what color combination, all those kind of things. So each of your friend would give you that opinion or advice. So 10 of them will give you different opinions, all right, their own personal advice on what you should get. So what you will now do is you now collect all their opinion and now look at everything. And you said my voice is fast. I don't know. This is how I have been speaking in the previous classes. All right, okay, fine. So you kind of couple the opinions from your different friends and just get the um combine everything to make up your own decision or to use it in your decision making. So that is what ensemble learning is. Ensemble learning doesn't just depend on one model, it depends on you creating different models and now combining their predictive power into making a particular prediction. All right, so you are not just relying on a single friend, you are relying on multiple friends, many of your friends, to give you advice on that particular problem, and then you combine it, their advice, and use it to make your own decision. So obviously, the advice of several of your friends would be better than the advice of just one single person. That's the benefit or the advantage of using ensemble technique. You are kind of combining the predictive power of different models, all right, to give you one particular prediction. So you know automatically that these different two more than two or more models will give you a better prediction than just one model. So that's the idea that is behind ensemble learning. So that is just a general overview or the intuition behind that. So ensemble learning refers to a machine learning approach where several models are trained to address a common problem, and their predictions are combined to enhance the overall performance. All right, so this is the aim of ensemble learning: combined prediction. Okay, at the end of everything, you still get one prediction, but there's a way it is combined so that you can get just one prediction as you would do in the previously where you are using just one model. So the aim is just to enhance the overall performance, so to give you a better prediction than when you are using just one model. The idea behind ensemble learning is that by combining multiple models, each with its strengths and weaknesses, the ensemble can achieve better results than any model alone. Okay, so it's just like the saying that we all know: two heads are what better than what one. So obviously, in this case, two machine learning model is better than what? They are better than one. They are better than one. Okay, so that is the idea that is being transferred into this ensemble learning technique. Okay, so it can be applied to various machine learning tasks, including classification, regression, and clustering. So whatever task it is that you want to do, you can apply this ensemble learning technique. So we are going to look at the different the techniques in ensemble learning, and going forward, we're also going to look at some of the algorithms that you can also use in ensemble learning. So let me still try to build your intuition up. The goal of ensemble learning is to improve the overall performance of the model by aggregating the predictions of multiple learners. Okay, so you can read this when you get the material. We're still trying to emphasize or lay emphasis on the core idea in ensemble learning. So let's just quickly move to the different categories. So several methods can be broadly categorized into two types. All right, so we have talked about ensemble learning, we've talked about what it means, right? So generally, ensemble learning can be categorized into two types. So I'm going to expand on these two types by giving some examples later on, but this is the general categories under ensemble learning. So we have parallel ensemble methods and we have sequential ensemble methods. Okay, so we have parallel ensemble methods and we also have sequential ensemble method. So what does parallel mean? You know what parallel mean, right? Parallel are actually when things are happening simultaneously. They're happening at the same time. Why sequential ensemble method or sequence or sequential mean something happening one after the other. So one has to happen before the next one, happen before the next one, happen. So that is what sequential, that's what we mean by sequential. Why parallel, it happens at the same time. So coming to ensemble learning, parallel ensemble methods are basically methods where the models are actually trained independently at the same time. And each of those model would give you a prediction, right? And those prediction can now be averaged, or you would use different techniques to actually get the single prediction, or collate the prediction from the different model and then generate one particular prediction that represents the majority of the models that you trained. So that is parallel. Everything is happening at the same time. The models are trained independently, right? Separate from each other. There's no connection between model A and model B. There's no connection between model 1, 2, model 1, 4, model 1, 5, model 2, 3. All of them are trained independently. But when we come to sequential ensemble methods are trained in sequence, all right, one after the other. So let's say you want to train 5 models. So you first train in parallel, you just train everything at the same time. There is no sequence to it. You get your prediction and your output, and then you collate it to generate one singular output. For sequential, you actually train them one after the other. You train model 1, the first model, and then you use the output, or based on how your model 1 performed, you will now train your second model. And then based on the performance of the second model, the weakness would be, it is going to now, the model 3 will now be trained to kind of improve on the performance of model 2. So in sequential ensemble method, there's a connection between the different models. There's a connection among the different models that you are training. While in parallel, there is no connection, right? They are separate, they are independent. While in sequence, there's actually connections in among the models that you'll be training, all right? So as you can see, your models are trained independently and their predictions are combined, right? So we'll look at how we can actually combine their prediction and all of that. So an example of this parallel is bagging. So we'll be looking at bagging. We'll also be looking at the other one, which is what boosting. So in sequentials, the models are trained sequentially with each new model attempting to correct the errors of the previous ones. So when you train model 1, the first model, you get a performance, all right? So the second model that will be trained will try to improve on the model that you trained initially, looking at where it made mistake and working on the mistake to get a better model. So it's kind of boosting it, right? That's why it's called boosting in this case. So we'll actually look at what boosting and bagging is. Yeah, as we move along or as we move ahead. Right. So but just notice are the two overarching categories in ensemble methods. All right, so that is it for ensemble. I believe by now you already getting to understand what ensemble learning is. So as I said, ensemble learning is not a machine learning algorithm. Rather, it is a technique that is used in machine learning. Right. So let's just move forward. And we're going to look at some techniques, in ensemble techniques. So this is not the ML algorithm yet. These are just techniques that can be used in selecting the final prediction. Okay? Ensemble technique. You remember that we are training several models, but at the end of the whole thing, we want to get just one prediction. So what are the techniques that we can use to get that one prediction? So we'll be looking at some of them here. The first one here is max voting. Second one here is what averaging, and the third one here is what weighted averaging. Yeah. So these are the 3 methods or 3 techniques that is used in selecting the final prediction in any ensemble learning algorithm, all right, in any machine learning algorithm that uses ensemble technique, or when you are using ensemble learning approach. So the first one, which is called max voting. So let's quickly look at it here and then I'll explain. So max voting is an ensemble technique used primarily for classification tasks. Okay. So when you're doing classification task, you actually apply or use the mass voting technique. So all these things I'm explaining now, as I said yesterday, you won't be actually implementing them. What I'm trying to do is just trying to give you an understanding of what the algorithm is doing at the back end, like what it is doing behind the screen and all of that, the computation that is being carried out. So this is the explanation. When you call your model, you import it from sklearn, and then you say model.fit. All right, this all these things I'm explaining now is what happens. So you don't have to write codes to do all this thing for you. Although you can try yourself to just understand it better, but it's not necessary. Okay, it's actually not necessary because tools and functions and libraries have been built for us to perform all this thing that we are looking at here. So don't try reinventing the wheel. That is one thing in programming. Don't reinvent the wheel. If something that can make your work easier has been done, then go ahead and just use it. So in this case, you won't be implementing any of this, right? It's just model.fit. You train your data. So during training, I just need you to understand what is happening as a data scientist. It's very important for you. So you might come to a point where you meet some errors that need you to have an understanding of that particular thing you are doing. If you don't, it's going to be a problem for you to tackle that particular error. All right. So let's continue what we're looking at here. We are looking at max voting, which is an ensemble technique used primarily for classification tasks. So depending on the tasks you are performing, whether classification or regression, we're going to use different ensemble techniques for getting the final prediction. So let's assume you want to predict let's use yesterday's example. You want to predict spam and not spam. Okay, you want to build a model that can predict whether an email is a spam email or what non-spam email, not spam email. Normally, what you would do with the knowledge you already have is what you just go and pick any classification model algorithm and build your model. Okay, so once you build your model, you can now evaluate and all of that. And if your model is fine, that's it. You've actually done what you need to do. But if you now try using the ensemble learning technique, the approach is different. Okay, so once you apply any ensemble learning algorithm, what happens is that multiple models are created, right? Multiple models are created. So it can be 10, it can be 20, it can be 50. Okay, so when after that those models are created, each of them will give you a prediction. Each of them will give you a prediction. And the way to select the final prediction is actually to get the maximum, the category that has the maximum vote from each model. Let's say from your 20 models, after you've trained it and everything, during training, let's say out of those 20 models, 15 of them predicted the particular data point or the particular data to be, or the particular email to be a spam email. That is, let's say label 1 in this case. And the remaining 5 models selected 0, which is non-spam. So automatically, you know that majority of the vote goes towards spam, right? Majority of the votes goes to spam, meaning that 15 of the models in the 20 models that is being trained selected spam or predicted spam. So that's what mass voting is. Mass voting actually select the highest number, okay, highest number, the highest class, the class with the highest number, and pick that particular class as the final prediction. So in the case of this example, the final prediction will be what spam, because majority of the model that were trained carried the the spam votes. All right, selected the spam. Majority of them selected spam, so the final output is going to be spam. So if it is otherwise, let's say out of 20 model you created, 17 of them selected non-spam, while the remaining three selected spam. The final prediction will be what? Non-spam. So you're actually voting. Their votes are being casted, and the vote in this case are what the prediction. So you get the prediction with the highest count and select that as the final prediction. That is what happens in max voting. And max voting, as I've said, is basically for classification task. You can't do max voting when you are predicting continuous variable. How exactly do you want to? You don't do max voting there. So we're going to look at the other techniques that can be used when you are doing any regression task. So as you can see here, max voting is an ensemble technique used primarily for classification task. In this method, multiple models are trained independently, and each model casts a vote for each class. So this casting that you can see here or that is on the screen is basically prediction, right? Each model makes a prediction. So the final prediction for a given instance is determined by the class that receives the highest number of votes from all the models, right? That is what happens when you're using max voting, or when the algorithm you're using is using max voting. So there's some key points here. Just go through it quickly. It's simple and intuitive. Model diversity. The ensemble benefit from diversity of individual models, as different models might make different errors. So it's possible that when you train one model, that model can actually make an error, an individual error, and instead of predicting one, it predicts zero. So that's an error. But when you're using multiple models, like, you know that yes, there will be some errors, but majority of the models should actually give you the right answer. So looking at majority and selecting your final prediction from there, it is more it will give you more accuracy, right? Than when you're relying on just one model, because you know that it's not possible for a lot of persons to fail something, majority to fail something. Let's assume you're in a class and you ask a single student a question, all right, an option question. Let's say you ask them which continent is Nigeria from, right? You give options and all of that. So the person picks an answer. It is possible that that person could be wrong. And the person could not really have an idea or make a mistake and pick another continent, maybe like Europe. But when you ask, let's say, 50 persons in that class, there's a low probability that majority of them would feel it. Do you understand? That is the idea. That is the core idea behind this ensemble learning. So if you ask 50 of them, even if some of them fail the answer, majority will still get that answer. And the answer you are looking for, the final answer you are looking for, is the answer that the majority selects. You understand? So that's the idea in this case. That is what max voting is. So you select the class that has the highest number of votes from the model. So look at the key points: robustness, applicability. It reduces the impact of any single poorly performing model on the overall prediction. So even if one model is performing poorly, it will not really affect the final prediction, right? Because you are ignoring it and focusing on just those ones that are part of the majority. That is the first technique here, which is max voting. The other one we have here is what we call averaging. All right, averaging. So what is averaging? Now, I said max voting is used when you are performing a classification task. Okay, so averaging is being used when you are on a regression task. Okay, so when you're in doing a regression task, you use averaging technique. So by now you should already be getting the idea of what averaging is. So in case of regression, you're predicting continuous variables, right? So let's say you have 20 models and they make their predictions. To get your final prediction, you just add up all the values, all the predictions from the different models and average them. So the average is going to be your final prediction. That's exactly what averaging is. No long talk, no long story. right? That is exactly what averaging does in ensemble learning. So averaging is an ensemble learning technique used primarily for regression tasks, although it can be adapted for classification, but don't even bother yourself about that, right? So, but in this method, multiple models are trained independently, and the prediction is obtained by calculating the average of the predictions from all of the models. So I believe that is actually easy to understand. So if you understand max voting, just flip it over to regression task and imagine how you also get the final prediction for models that are predicting continuous variables. You can actually do use max voting for continuous variables. So what are the key points here? Continuous predictions, right? It's suitable for regression problem where the output is a continuous value. Stability, averaging prediction can smooth out the noise in individual models, prediction leading to more stable and reliable results. Model independence, right? So, and error reduction. So these are some of the things, some of the strengths of using averaging. Now, these things you will not be implementing them. I just want you to keep that at the back of your mind. So, is when you are selecting a particular ML model, you'll know that okay, this is a technique that this particular algorithm is using. Right? We look at random forest, we look at SGBoost, we look at other boosts, we look at some of these things, and they use their different techniques in getting the final prediction. So I just need you to understand this. So the last one here is weighted average. So weighted average is basically the same thing as averaging. All right. The only difference here is that weights are assigned to the predictions of each model. All right. So let me just give an instance, right? An instance that can help you understand this. So still assume that you're in your class, you are the teacher, right? And then you call 50 students. Okay. And out of all these 50 students, you know the capacity of each of the students. You know your best student, you know the top performing student and all of that. So when you are asking them for predictions or for answers, you not just get the answers and average them. All right. You not just get the answers and average them. What you do, in this case, it is a regression task or not classification. In this case, you actually add something to each of their answers. You add what we call importance. So to your top student, you're actually going to give your top student answer a greater weight. So when you are averaging them, the answer of the top student will have higher level of importance. It will have higher effects on the final output, because you know that this person answer is likely going to be correct compared to, let's say, other persons that are not really on the they're not they're not performing well in the class. So you put less importance to those set of people, to their answers, and you put more importance to the answers of your top students. So that's what we call weights. So those weights is going to determine how much effect the prediction of each individual model we have on the final prediction. That is what weighted average is, right? So there is a particular model that uses weighted averaging. So we're also going to look at that. So we've looked at the techniques used in selecting final prediction here. We looked at max voting, okay, which is used for classification task. We've looked at averaging, which is used for regression tasks as well. It doesn't have any weight attached to it. It's just you're just getting the predictions and getting the average like that. But for weighted averaging, you're actually considering each of the prediction and how much effect that we have on the final prediction. So you add weights. Weights is actually value. In machine learning is a value, right, that you can multiply with the prediction, right? So that's just it. That's actually just it. So see the key points for weighted averaging: performance based. So weights are typically determined by the performance of each model, as I said. So the weights will be determined by the capacity of your student. If that is your best student, you give that best student the predictions or the answer of that best student a higher weight. So when you multiply it with your answer, it's going to have a higher value and all of that. So flexibility, with better performing model receiving higher weight. Flexibility. This technique allows for flexibility in emphasizing more reliable models with. So all these are just the advantage or the benefit of using this particular method. Improved accuracy. Weighted averaging can further improve the accuracy of the ensemble by giving more importance to the more accurate models. Okay, and then complexity, right? So determine the appropriate weight can be complex and may require validation. So these are just the things to know about weighted averaging. So we'll just look at the summary of these three techniques, right? So for max voting, it is best used for classification problems where a consensus decision among models is desirable, right? It leverages the majority opinion and works well when there is significant diversity among the models. So I've already explained what max voting is and how it is being used. So this is just an extra information, right? Or saying the same thing basically. Why averaging? It is ideal for what? Regression problems. Okay. So where the goal is to predict continuous values, it smooth out individual model variance and provide stable prediction. So these are just the things that averaging does to your final prediction. So for weighted averaging now, weighted averaging can is actually also suitable for regression task. All right, so you can also as well use it for classification task, but it is mostly suitable for regression tasks. So there are some things that you need to do and all of that to adapt it, but just pay attention or focus more on the regression aspect, especially when models have varying degrees of what performance, as I've said. The models have varying degrees of performance, yeah, the weighted averaging will be the best. All right. So it allows the ensemble to capitalize on the strengths of better performing models. So I believe that has explained itself. So in summary, ensemble techniques uses such as mass voting, averaging, and weighted averaging provide a robust approach to improving model performance by combining the strengths of multiple models. Right, so these models are widely applicable across different types of machine learning tasks, as we said initially. All right, so can be applied to regression, to classification, to clustering, which is unsupervised learning technique. All right, so that is it. We've actually looked at some few things here. We looked at ensemble learning. We looked at what ensemble learning is. We looked at the general classification of ensemble learning or ensemble methods. All right, now we went on to look at the ensemble techniques, which are the techniques used to getting the final prediction of your model. Okay, we looked at max voting, averaging, and weighted averaging. Now we're going to look at um, two methods in ensemble learning. Now, remember we looked at two categories here. These two now is the same thing as what I'm about to explain here. So these are just they're the same thing basically. So don't get confused. But we use bagging. A bagging is an example of this parallel method. Bagging is an example. So we are bringing out bagging and elaborating on it. For sequential, boosting is one. So we are bringing out boosting and elaborating on it. Okay. So we are going to look at bagging, and we're also going to look at boosting. Okay. So these are the two things we're going to look at today, and then we're going to wrap it up. So what exactly is bagging? Bagging basically mean bootstrap aggregation, right? Bagging means bootstrap aggregation. So if you just bring out the B here and add it to this aggregation, you get bagging. So the ing is just to make it sound well. So that is basically what bagging means, bootstrap aggregation. So you have to know what bootstrapping mean, All right, then you also have to know what aggregation means to understand bagging. So let's look at it. Now, bagging is, as we have said, short for bootstrap aggregation. It's a method in machine learning where we use multiple versions of a model to improve its performance. And these things are actually things I've explained already, right? But we're going to see the difference or what makes bagging unique or different from other methods that we're going to be looking at. Okay, so bagging is like a parallel method, as we've said, where you train individual models independently and then you get their predictions and then you kind of aggregate their predictions to get one final prediction. So there are steps in the bagging process. So we're going to look at them. So we have the first one, which is model sampling, sorry, bootstrap sampling, followed by model training, all right, and then followed by aggregation. So these are the three steps in bagging. Very, very simple steps. And I've actually said something about it. So this is just me kind of repeating myself, but in a more specific way and being more specific, right? So the first step in bagging is bootstrap sampling. What does bootstrap sampling mean? So someone suggested that there are some things that there were some words they had in class that they've never had in their life before. That was actually very funny. So you would hear a lot more today, right? So in case you haven't heard about bagging before, that's going to be another new word in your vocabulary. So now bootstrap is another one as well. But if bootstrap is a general terminology, sure. So, but if you have not heard of bootstrap, then it's fine. So what do we mean by bootstrap sampling? So bootstrap is sampling is actually a method of sampling from your data. All right, a method. Can everyone still hear me? I need feedback. Can everyone still hear me? Okay. All right. Okay. Fine. So we are going to look at the steps, as I've said. So the first step here is bootstrap sampling. What does bootstrap sampling mean? Bootstrap sampling is where you actually create subsets from your data set. Remember, you want to train multiple models. So what bootstrap sampling does is that it selects or creates different subsets of data from your data set. So imagine you have a bag, and in that bag you have different numbers. All right, you have different numbers. Like let's say you have from number 1 to 100 in that bag, and you want to create bootstrap samples. All right, how you do it is that you let's assume the bag is something you cannot see inside. You can't actually see what is inside. So you get the bag, and then just let's say the number was written on something, right? So you shake it to make it random, right? So that you have no influence over the particular number you are picking. So the thing you do when sampling or doing bootstrap sampling is that let's assume each sample or each subset should have let's say 20 data sets or 20 samples from your data set generally. So what you do is you shake it to make it random, right? And then you put your hand inside the bag and pick a particular number. All right. Once you pick that number, let's say you pick number 5, you write it out. This first subset, the first number I picked is 5, all right? Then you don't throw that 5 away or keep it aside. You actually put it back into the bag again and then shake it to ensure that it is random, that your selection is random. So once you do that, you then pick another number again. Let's assume the second number you're picking is 10. Then you write it under subset 1 that you've picked 10. So you do that process and you repeat it 20 times to create 20 samples. So once you've created 20 samples, that is your subset 1. All right. So then you've created your first subset, and let's assume you want to create 5 subsets because you want to train 5 models. In bagging, you're actually training your model on different subsets of your data sets. You understand? You're not training your model on the entire data set. You are creating several subsets from your data set through bootstrap sampling, and then training each model on each of those subsets and getting a prediction. That's what bagging is basically. So in bootstrap sampling, as you can see, as I've explained, you create several new data sets from the original one by randomly picking samples with replacement. So this with replacement is very important, right? So that means you can actually repick a particular data or a particular sample, right? That is what it does. You pick a sample, you note it, and then you put it back. You can actually pick it again, but just make sure that the process is random. So this basically means that some samples may be picked more than once and some may not be picked at all. So each new data set is called what? A bootstrap sample. So it is on that bootstrap sample that you are going to now train each of the ML model in your bagging using bagging technique, in your ensemble technique or ensemble algorithm. All right. So you do that. Let's assume you are creating, or you want to train 5 models. You create 5 bootstrap samples, and then the next step is what? Model training. So what happens during model training is that each model that you will be trained on each of the bootstrap sample. All right. Each model, you train separate model on each separate bootstrap sample. Right. So these models are usually of the same type. So if you want to use decision trees, you make sure that you are using decision trees for each of the training. You can't mix different models. You have to use the same model, right, multiple times on the different data set. Right. So that is basically what happens. So that's the second step here. So you get your samples, you train your model on each of the bootstrap sample, and then the final step is what we call aggregation. Aggregation can either be done based on the task. It can be done for regression, and it can also be done for classification. So as I've explained already, for regression, the final prediction is the average of all the individual model predictions. While for classification, the final prediction is determined by a majority vote among the individual model predictions. So these are the 3 steps in bagging. Very, very simple. Very, very simple and straightforward. So first thing is you get your bootstrap sample. And as I said before, and I'm going to be repeating myself, you are not going to be doing these things. These things are being done behind the scenes, right? When you are training your model, right? So the model that that have been created already, they perform all these things, but it's good that you know how they work. You can actually do it yourself. If you know how it works, you can actually create a model from scratch using pure Python on your own. All right. So as a data scientist, you need to know all these things. You need to actually know how they work, not just how to use them or how to use a library. All right. So that is it for bagging. Now, why do you use bagging? So yeah, as I said, I'm not going to focus on this because I've not explained overfitting. So basically, bagging reduces overfitting. All right. It improves accuracy, and what it increases robustness. Okay, so these are the 3 benefits. Obviously, they should have benefits because you are actually using the predictions from several models to get your final prediction. So the next thing we're going to be looking at, okay, let's just look at the conclusion here. Okay, you can read that when you get the material because of time. So the diagram here is just going to be illustrating what I've been explaining since. So you can see this diagram. I don't know Just trying to zoom out so you see it clearly. So this is bagging now, which is an ensemble method. Okay, this is bagging. So this diagram explains exactly what happened. You see this first step here, step one, is where you create subsets of data. All right, data subsets from your original data. Okay, so you have, let's say in this case, you created four. Create subset one, subset two, subset three, subset four. And for step two now, for each of these subset, you will now train in an ML model on this data. You train it separately, you train another one on the second one, train another one on the second one, train another one on the third and fourth one. And then you now aggregate it, the prediction from the different models to get your final prediction. So in ensemble learning, we call the models the weak learners. We call them weak learners, or that is what they are called. In case you see it anywhere else, you know that yes, these are actually models that are being used in an ensemble algorithm. So we call them weak learners. Okay. You would also see in sklearn, we would be using what we call estimator as the terminology, or sklearn uses estimator. So when you see estimator in sklearn, just know that estimator refers to what? The model that you are using. Estimator is what you are going to be seeing in sklearn, which refers to what? The model that will be used in training, right? So decision tree algorithm can be an estimator, logistic regression can be an estimator, linear regression can be an estimator, KNN can be an estimator, SVM can be an estimator. All right, so that is basically what estimator mean, right? So I'm saying this now because when we start the implementation, you're going to see all of that. So that is it for bagging. That's it for bagging, the 3 steps in bagging. Now, there's a particular algorithm that uses bagging. There's a particular algorithm that uses bagging, and this algorithm is a very popular one, and it is called random forest algorithm. Yesterday, I told you that you need to understand decision tree, right? Because there is an algorithm we're going to look at today, which uses decision tree. So random forest algorithm is an ensemble of what? Multiple what? Decision trees. So think of it this way. Decision tree is a single tree. Random forest. Forest is what? An aggregation of what? Trees. An ensemble of what? Trees. So if you have, let's say in your backyard now, you have a single tree in your backyard, you know that, okay, yeah, this is a single tree. This is a single model. But if you go to your village, you will see multiple trees. So you term that particular area as what? Forest, because they are what? They have multiple trees. So the same thing applies in ML. So we have decision tree algorithm, which uses a single tree in prediction, right? In a single tree during training. Then we'll have random forest algorithm, which uses like an ensemble of multiple decision trees, or uses multiple decision trees in doing this prediction and all of that. So let's just look at it quickly. So random forest is a powerful ensemble learning method that builds multiple decision trees and merges them together to get a more accurate and stable prediction. So all this thing I've been saying before in bagging and all of that, it's the same thing here, but there's something specific to random forest. All right. So random forest, as you can see, it's a type of bagging technique. All right. But with an added twist. There is a twist. There's a thing that is being added to make random forest, right? Random forest now doesn't only take bootstrap samples. Doesn't only take random bootstrap samples from the data set to make subset, but it also uses a random subset of features for building each tree. So now it is using a combination of two random things It is using a combination of random data set and a combination of random features. So what do we mean by that? Let's assume in your data set you have 20 features. Okay. In your normal bagging, the idea of bagging itself, you just get from those 20 features, you get random subsets. So each subset we have 20 features. That is the idea of bagging generally. But in random forest now, random forest algorithm doesn't would not use all the features for each subset. As it is getting random subset, it's also getting random features as well for each subset. So subset one could have feature 1, feature 2, feature 10, feature 15, feature 13, feature 17 randomly. Subset 2, we have another set of different features. Subset 3, we have another set of different features like that. All right. That is what makes random forest unique. And it also makes it actually powerful because now you are actually training your model not just on random subset, but also on random features. So each of these things, each of this model that will be created would have advantages based on the feature that they are being trained on. All right, so that is random forest for you. Okay, so as you can see here, this additional randomness helps to reduce the variance and prevent overfitting. You've been hearing overfitting and all of that. Don't worry, we're going to go into it in the next class, right? Next week. So it makes it one of the most popular and effective machine learning algorithms. So random forest is actually a very powerful ML algorithm, very, very powerful. Right. So what are the key features of random forest? So it has multiple decision trees. As I've said, it uses bootstrap aggregation. Okay. Random feature selection, as I just explained now. That's high accuracy and handles overfitting. So these are the features or the things you need to know about random forest. Well, now what are the steps in building a random forest? So these are the things that happen when you call random forest model.fit on your data. You first select random samples from the original data set and select random samples. Okay, this sample replacements, right? So this random sample selection is happening concurrently with the random feature selection. Okay, so once it's able to get the random subset, the bootstrap sample, then it now builds decision trees, use decision tree algorithm to build a model for each of those subsets, and then it gets the predictions using either averaging or what majority voting, which is max voting. So yeah, this is the code implementation. Just straightforward. Okay, we're going to look at that. So let's quickly look at the other algorithms that we have here because of time. So this diagram will show you what a random forest looks like. So if you are familiar with the decision tree that we did yesterday, if you remember what we did, this is an individual decision tree. All right. In random forest, we have multiple of them. So we have one, we have two. In this case, we have three. So each of them will make a prediction, make a prediction, make a prediction, and then if it's classification, we're going to do majority voting to get the final prediction. If it's averaging, so that is basically just what happens. So this is a diagram to illustrate what is happening under the hood. All right. So that's it for random forest. Random forest is what an example of bagging algorithm. Random forest is an example of bagging algorithm. Now we have boosting. So boosting is the second method or the second ensemble method that we looked at, which is an example of the sequential ensemble learning. All right. So I explained what sequential ensemble learning does. All right. So it's the same thing that applies here in boosting. So boosting is an ensemble learning that aims to create a strong classifier from a number of weak classifiers. All right. So so it aims to create a strong classifier from a number of weak classifiers. So unlike bagging techniques, e.g. random forest, which create independent models and combine their results, boosting train models sequentially. So you need to know this. This is what boosting does. It trains it sequentially. It trains one model, and then when that model is being trained, it look at the performance and look at where the error is, and then tries to improve on that error by training another model that will capitalize on that particular aspect where the error is made. So the second model will be a more powerful version of the previous model. So this thing repeats itself till you get to the final number of models that you want to create, that you want in your algorithm, all right? Or you want in your final model or in your ensemble model, right? So the terminologies are just everywhere. So that is it for boosting. It trains models sequentially. As I've said, each model attempts to correct the errors made by the previous model. So this thing I just highlight now is the hallmark of boosting. This is the if you can just know this, like you don't even if you don't remember any other thing, if you can just know this, you already know what boosting is. All right, this is it. Each model attempts to correct the errors made by the previous models. That's the aim in boosting here. So the primary idea behind boosting is to focus on the mistakes made by previous model, thereby improving the overall model and performance. So that's what boosting is like pushing something to be better, pushing it from a state that a lower state to a what higher state, from a lower accuracy to what a higher accuracy. So just that idea of boosting is what is being applied here as well. So for bagging, you know what bagging is? Bootstrap what aggregation. It trains model in parallel, independent of each other. They have no connection to each other. No one is learning from the mistake of another one. That is what boosting is all about. Sorry, that's what bagging is all about. But boosting is different, and it trains model sequentially by focusing on the mistakes made by previous models. Okay, so let's look at the key features of boosting. So we have sequential learning. So models are trained sequentially, with each model correcting the errors of the predecessor with adjustments. Misclassified instances are giving more weight to subsequent models. So this thing that is here is just telling you exactly how the boosting algorithm attempts to focus on the mistakes made by the previous model. So now we also have model combination. Predictions from all models are then combined, often using a weighted sum to produce final prediction. So there will still be a combination, right? Each of the models, sequential model, from the first to the last, would have their prediction combined, but in a weighted manner. So obviously, the final model will have higher weight than the initial model because the final model it has learned the mistakes of all previous models. So it will be given higher importance, right, in affecting the final or making the final prediction. So that is it for this. So obviously, it will have high accuracy. All right, it is going to have higher accuracy. Now we're going to look at the types of boosting algorithms. We looked at the type of bagging, which is random forest. So that is the major one. That is a common bagging algorithm. So we are going to be looking at the different types of boosting algorithms. So there are a lot of them actually. We are going to look at just two of them or three, if time permits. So we have AdaBoost. We have AdaBoost, which basically means adaptive what boosting. So it's not Ada as like the Igbo name given to the first female child. It is adaptive boosting. Okay. We have gradient boosting. We have SG boosting, which is usually the best. This one, let me just give you a spoiler alert. SG boosting is like usually the best model out of all the ML model that you've seen. In competition, SG boost is the model, the go-to model in winning a lot of ML competition online and all of that. So SG boosting is just very, very good, very, 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 very good. Right. So we have light GBM. So all these ones are just other variations of the boosting algorithms. So we are not going to look at. We are just going to look at AdaBoost, gradient boosting, and SG boost. Right. So I hope we have enough time for that because I said I want us um to finish on time here. So I'm actually looking at time. So yeah, let's just proceed. Let us proceed. So we looked at how bagging works, right? Looked at the steps, the three steps in bagging. We're also going to look at boosting as well. We are also going to look at boosting. So please let me know if everyone is still following. I need all right, all right, all right, all right, that's fine. That's fine. So now we're going to look at the steps in boosting. Okay, so boosting is a little bit more nuanced and complicated than bagging. Bagging is straightforward. So let's look at it. So in the first thing that happens in boosting is weight initialization. So each of the training samples, right, they are given what equal. Well, some people questions having please just give me a second. Okay, all right. So okay, let's quickly look at this. So during boosting, the first thing that happens is weight initialization. So each all the training samples. Now for bagging, remember bagging, we are creating subsets of data. It's not the same thing here in boosting. Boosting, we use all the data sets at once. We're not creating any bootstrap sample or any of those things, okay? We are working with all the data sets at once. But something is being done, something has to be done first. Each of the training samples, if you have like 1,000 training example, each of them would be given equal weight. Okay, they'll be given equal weight. So by now you should already know what weight is. Weight is like something that is used to attach value or importance to something. So at the beginning, every training example is given equal weights. Okay. So after you've done that, then you now train that data set with a simple model. You can use decision tree, you can use logistic regression, you can use whatever it is that you want to use, whatever model that you want to use. Okay. So you train, and we call it a weak learner. Remember what I said initially? It's the weak learner. So we train a weak learner on the training data set that has been weighted. Okay. After you've trained that, then you now evaluate the performance of that weak learner, of that model on the training data itself. All these things they're happening during training. No, you are not doing anything. When you just say model.fit, these are the things that will happen behind the scene. Okay. So it will now evaluate the model performance on the training data. And then when you evaluate it, it now looks at those particular training examples, right, that were misclassified or that had those places that had errors. Now, so the algorithm would now increase the weight of the misclassified samples, right, of those particular samples that were not predicted accurately. It will now increase the weight so that the next model would actually focus on those samples so as to create or make a better prediction or not to make the same mistake as well. So the weight is being updated. Remember, at the beginning, everything has equal weights, but in the next iteration, the weight is being updated with the misclassified samples having higher weight or greater weight, right, to emphasize their importance in the next round. So after you've done the weight update, then you now train and the next week learner with this new weight that you've already that has been updated. Okay, so once you do this iteratively, let's say you do it 5 times, after you've created all this model, you have several weak learners. Okay, and then you now combine them using your normal aggregation. So you can use it if it's classification, you use voting, if it's regression, you use average. So that is just the idea behind boosting. Okay, it might not be as intuitive or easy to understand as bagging, but this is what it does, right? So it's actually more it gives more accuracy than most of the time than bagging because it's improving on each model. It's each model iteration is a better version of the previous model. All right, so that is it here. What are the advantages of boosting? Improved accuracy, right? Flexibility, reduction of bias. So you can just look up all these things yourself when you get the material. And let's also look at the disadvantages. It is sensitive to outliers. All right. So boosting can be sensitive to noisy data and outliers as it tries to correct all errors, including those caused by noise. So if you have a data set, a data point in your data set that is an outlier, it would actually affect it would be sensitive to it, right? To affect the output of your model. So you need to ensure that you clean your data very well before bringing it into this using boosting on it. It's also computationally intensive, right? Training multiple models sequentially can be time consuming and computationally expensive. You'll see this when you try using XGBoost on a large data set. You're going to take a lot of time just to train a model. You'll see it. Right. So that's it for boosting. So we have several examples of boosting as we've talked about. So we're going to look at how to implement them in sklearn and we'll wrap up and call it a day. So let's look at the diagram to explain this boosting algorithm. Or else let me zoom out. So you can see now this is boosting, all right? So you have your input data set. So you are not separating it, you are not creating subset of your data set, you're using the complete data set. Now, this is the first week learner, as you can see here. This is the first week learner. You train it on all your data sets, and then you now adjust the weight. But initially, you create equal weight or initialize each of the samples or the observation with equal weights, and you train it on your data set. Okay. Once you train it, then you now update, you now evaluate it and look at those particular samples that were misclassified, right, or had errors, and then you now adjust the weight by giving more weight to those samples. And the adjusted weight will now be used in training the second weak learner or weak model on the complete data set. So you can see how the arrow is pointing down from this, and the weight that is coming in is the weight from is the knowledge from this previous model that was trained, right? So that the same thing happens iteratively until you get to the last model, let's say in this case, the fourth model. So the fourth model is being trained and each of them is now combined. Right, they have their predictions, all of them we can see here, and you can use aggregation method by voting or averaging to get your final prediction. So that is it. That is it for boosting. This is a diagram. Once you get the material, you're going to see it and appreciate it better. Okay, so we have XGBoost here, which we're going to look at. So we'll look at all of them individually, but let's start with random forest. So Now let's open our explanation sheet so implement all of this that we've been talking about. All right. So what we'll do first is just to import um, models. So I'm going to be using classification now as an example. So when you get the material and all of that, you can try it on a regression task. Importing algorithms. So for we have the random forest. So to import random forest, you come and say from sklearn dot ensemble, right? Ensemble import random forests, random forest classifier. Let me just confirm. Random forest classifier. So you can see it here. I also import my other boosts. I want to import everything at the same time so that you can just do it at once. So import other boost and which other one? Yeah, gradient boosting as well. Okay, so from sklearn dot ensemble. So ensemble is actually the module that has all these ensemble algorithms. So come and say other boosting classifier, and you can just say gradient boosting classifier as well. So you run that, import data sets or data set rather, because we're just using classifier. So you come from sklearn dot data set, import load breast cancer. All right, so then importing metrics, importing metrics. So this is a classification task, so you can just say from dot metrics import. So I'll come in and say precision score, recall, accuracy, confusion matrix, classification report. So these are the things we'll be using now. Next, we'll still look at ROC curve. in the next class how to use ROC curve and AUC to compare different models. So run this. All right, so we've imported the necessary things we need to import. Then let's start with the first one. Let's load our data first. So setting up of our no Shamsuddin. No, the matrix doesn't have to be in the bracket. It's just for a clean code. Can actually have them. Can actually have the metrics to be like this from sklearn dot metrics import precision score import recall import accuracy import classification import. You can see how the thing is now spilling over, right? It is not neat because you're importing a lot of things from one particular module. Is better you just put them in a bracket like this, so when someone looks at it they can say, oh, these are the things this person is important, rather than just writing everything in a long list like this. Understand? So it's just for having a cleaner code, so you can have it any way you want, anyhow you want. So here we'll get our data set. So we still have to import train test split. So from sklearn.model selection import train test split. Okay. Now we'll come and say data equals to load breast cancer. All right. All right. So I wanted to leave this till the next class, but when you are loading your data from sklearn, there is something you can actually do to have it presented as a data frame. If you leave it like this and you come and say x equals to data and what y equals to what data dot target. If you leave it like this and you come here and you kind of print out your x, you get something like this. It's an array, so you can't really read it, but this is actually okay for your machine learning model. But if you want to do exploratory data analysis and just look at your data to make sense of it, you can actually add a parameter in this your load data sets function to make it appear or come to appear as a data frame instead of a numpy array as this. So we have what we call as frame. So as frame is a parameter. By default it is false, but you have it to be true. If you change it to true, then once you load your data sets, let's say it's still loading, and you come here and you print it out, you see that it is giving you a pandas data frame. All right, unlike the array that you got there. So it's going to make more sense having it like this. So remember in the last class, I actually walked us through the manual way of doing it, that you just get the X and you do PD the data frame with the values and then the column names, right? So those it's necessary that you see that step too as well. But a shorter way of getting it to appear as a pandas data frame is by adding this extra parameter here as frame equals to true, right? So if you do that, your data would appear as a data frame. So I come here and say dot head. Okay. You can also come here and print out y. So y would be a series. Okay. So that is it. It's important that you know that. So we've loaded our data set. Now we are going to split it. So as usual, x train, y train, s test, y test. Is this how it's supposed to be? Sorry, this thing confuses me almost all the time. Should be x train s test. So we have should be S train S test and then Y train Y test. All right, so you have train test split function. All right, so you come here and you have your X and you have what your Y. Then you have random test size equals 0.2, and then you have random state equals, let's say, whatever number, let's use 40 today. So you run that, you have your data set ready for training. Next thing here is now to train your model. So come and say training model with random forest algorithm. So first thing first, you have to initialize your model. Come and say rf random forest model equals to random forest classifier. All right, so there are things that, okay, today is just for introducing you to algorithms. When we, in the previous class, in the subsequent classes, we're going to be looking at what we call parameters, right? I've explained what parameters are. The parameter is a very important thing in machine learning. Now we also have what we call hyperparameters. We also look at that. So we have some things that we can use to actually tweak the output or the performance of this random forest classifier. As you can see, the first one here is N estimators. So can someone remind me, what did I say an estimator is again when it comes to ensemble learning? Hello? What did I say an estimator is when we come to ensemble learning? I need more responses. All right, all right, all right, all right. So I just needed us to be on board with what we've been talking about all this while. So the estimator is what? An estimator is a single model. All right, it's a single model in the ensemble of models. So in this case, as you can see here now, in these parameters that we have here, we have n estimator as a parameter, which basically means number of estimators, number of models to use. So the default is what? 100, right? What do we mean by this now? It basically means that we have 100 decision forests. Oh, sorry, I said decision forest. 100 decision trees in this forest classifier. 100 of them. Understand? So out of 100 of them, we are going to be taking the vote of the highest class from 100 of them. Just scroll down, you will see the explanation here. You see the parameter n estimator, which basically means the number of what? Trees in the forest. You see how they put it there? The number of trees in the forest. All right, so that is it for random forest. So I just wanted to explain that. So I can come here and actually change it. N estimators. By default, it is 100. But if I want to change, I can change it to what? I can change it to 500. I can change it to 500, which basically means I have 500 decision trees. I can change it to 1,000 self. You understand? So I can change it to as many number of decision trees as I want. But just know that the higher the number of estimators, the more computationally expensive the operation will be. Okay. So in this case, let me just make it 50 decision trees. So I've initialized my model. I can now come and say rf model dot what fit and say s train y train. So once I do this, all those things I've explained, they happened in this particular thing that was this process that just happened, this training process, or everything I explained just happened now. All right. So if I come here and say rf model dot predict, and we have x what test, can come and say y grade. So you see we have accuracy, or let's use classification, or let's say use confusion matrix first. Confusion matrix. We have y test and what y grade. So you can see the confusion matrix, just 5 of them were misclassified. Just 5 were misclassified here. All right, so that is the random forest algorithm being used here. So that is just it, right? So there are some things we'll still have to expand on in subsequent classes when we start doing hyperparameter tuning and all of that. But everything I explained under random forest algorithm just happened. They actually were inside this rf model.fit. They were happening here. If I increase this thing to 100, if I increase it to 100, you see it will take a little time. You see, if I increase it to 200, it will take more time to train because it's training more trees. If I increase it to 300, it will take more time to train again, right? So depending on how much accuracy you want, you can actually increase the number of estimators. But just know that there's a point you get to that increasing the number of estimators will actually make no difference again, right? You would actually see it in action when you are practicing, right? Increasing the number of estimators at the point to actually have no effect on the performance of your model. So this is it for random forest. No more big deal. Just this, import your random forest classifier and do it. So you can actually do the same thing for regression task. You import random forest regressor, as you can see here, import it and do the same thing. Just make sure that your data set is aligned for that particular regression task. So let's go to the next algorithm we have talked about, which is adder boost. So using adder boost. Now, there's a very key point I need you to pay attention to or to note. Adder boost can actually use any it can use any ML algorithm as its base learner or as its estimator, right? In this random forest now, we are using which particular algorithm is being used as the estimator. I need an answer for that. I just want us to flow quickly to be sure that we are still on board. Which estimator was used in random forest algorithm? Exactly. Decision tree is the estimator used in random forest. And we cannot change it. We actually cannot change it. If you come to the parameter here, you won't see any option to actually change the estimator to another thing. It's by default uses decision tree as the estimator. But adder boost actually can use other kinds of estimator. It is the only algorithm here, like that we're going to look at, that can use other kinds of estimators. So let's just look at it. Let's say other model. Let's initialize it and say other boost classifier. Now we're going to look at the parameters with your shift and tab. So now you can see the parameters here. What do we have here? Estimator. So we have a parameter that we can indicate here, estimator. So this estimator what is the model we want to use in creating our boosting algorithm, right? So we can use any estimator that we want. We can use any classification algorithm we want. We can use decision tree. So let's just import all of that. I'll come and say from sklearn.tree, import decision tree classifier. From sklearn.svm, import svc. From sklearn.linear model, import logistic regression, right? So these are the okay, we also have knn from sklearn.neighbors, all right? Import k nearest neighbor, nearest neighbor classifier. So we've actually imported different classification algorithms, different classifiers basically. So we can now use any of them as estimator in Adaboost. So I can come here and initialize decision tree. I can come and say tree equals to decision tree classifier. I will say for logistic regression, I'll say log logistic regression. I'll say knn, come and say kn classifier, svc, right, svc. So I've already initialized different classifiers here, and I can now add them as an estimator in this place. So if I come here and include that parameter, that estimator parameter, I can say estimator equals to any of them. I can say estimator equals to, let's use logistic regression and use log, right? And then I can put another parameter, which is n estimators. So this n estimators basically mean how many number of logistic regression model do you want to build? How many logistic regression model do you want to build here? All right, that is basically what these n estimators here mean. So n estimators, come here and say, let's say you want to use 20. Let's see how many is the default here. The default is what, 50, okay? But we can change it to 20, or let's make it 100. Now we've used decision logistic regression. Then we are going to say other model dot fit to our train x, train y, train. So I'm going to do this. So all these things are just warnings, basically, just telling you a number of iterations and all of that. So I can change it here. I can come here and say n iters. What's the name of the classifier again? Max iter, right? Come and say max iter equals to, let's say 500. Let's see if it will give us error. Still giving us, let's make it 1000. Let's see. So all these things are just you tweaking the parameters to get what you want, right? So you are changing the max iteration in this logistic regression model that you are passing into this Adaboost, all right? So you can change this log to what? KNN, and it will use KNN for you. You can change it to what? Tree. Actually, by default, it is using tree. If you not include any estimator here, if you don't include any estimator parameter, by default, it's going to use decision tree. But if you do, you can change it to anyone. You can change it to support vector classifier, all right, KNN, logistic regression, or any other classifier and classification algorithm that you want to use. So that is it for Adaboost. So the process of getting your um, um, accuracy and all of that is still the same thing. Okay, so that is it. As you can see it here, it has trained already, right? It has. If you break it down, you see that it is using logistic regression as the estimator here, right? So I'll come here and say ada model dot. Okay, I'm not just because of time. I will not do the prediction. You can do that yourself. Let's quickly look at the next one. We'll look at gradient boosting. So gradient boosting is not like other boost. You cannot specify the estimator. It automatically uses decision tree estimator. So I'll come and say grad model is called a gradient boosting classifier. So if I open it here, you see it basically doesn't have any estimator parameter. It only have n number of estimators here, right? It uses the decision tree by default. All right. If you read all this thing, you see that it uses the decision tree by default. So just come here and say grad model dot fit x train y train. So everything I explained under all these things, that is what's happening during the fit or during the training process. All right. So it's very, very simple to use them in sklearn, straightforward, but just know the one that you want to use. Now we have the last one, which is very, very important. It is called SG Boost. Very, very important. So I told you how important SG Boost is in ML competition. So SG Boost is gradient boosting on steroid. I did actually explain this boosting algorithms, right? So let me just quickly go over them. But it follows the boosting, general boosting concept that I've explained already. So ADA boost is one of the earliest and most straightforward boosting algorithms. It adjusts the weight of misclassified samples, giving them more importance. So it uses the same idea that I've explained already. Gradient boosting. Now, gradient boosting, it also builds models sequentially, where each new model tries to correct the errors made by the previous model. It uses gradient descent to minimize the loss function. That is where it gets the name gradient boosting. So there's what we call loss function in ML. That is basically the function that calculates the error of your model, because you are trying to minimize the error as much as possible. So that loss function is what your model is trying to minimize. And in the case of gradient boosting, it is using gradient descent. Gradient descent is an algorithm, an optimization algorithm. So don't rack your brain around. Don't get worked up hearing all of this. You'll get comfortable with them, right? We are not looking at gradient descent, but this is where gradient boosting got its name from, and this is what makes it gradient boosting. So for SG boosting is like an advanced gradient boosting. It has a lot of things going on that makes it much more better. All right. So we will not look at that. There are a lot of technical things, there are a lot of details that you need to understand to fully grasp SG boost. But just know that it is extreme. The X here means X extreme, G here means gradient, and then you can just know it as extreme gradient boosting. So that's basically what SG boost, gradient boosting, and other boost. So if you understand the concept of boosting, understanding this won't be a problem. So let's look at SG boost. How do we use SG boost? So SG boost doesn't come in sklearn. That is the first thing to know. If you come here, you can actually import SG boost in sklearn. So if I give you an assignment to use SG boost, you have to import it. Sorry, you have to install it. You have to actually install it into your Python environment. All right. So how do we install it? We use this command, exclamation mark, pip install SG what boost. So this is the command you're going to type into your Jupyter notebook to install SG boost. If you don't do it, you are going to get import error when you try to import SG boost. All right. So if you come here, you can see that we can actually import it by just saying import SG boost as SGB. There is no sklearn here. All right. There's no sklearn, just SG boost like that. So I think I already have it on my system. So if I import it, I come here and say import SGBoost as SGB, or if I can just come and say from SGBoost import SGB classifier, because you want to use the classifier. Okay, so we've imported it. I already have it. I already have it installed, so I don't need to install it again. But for you, you have to run this command. So let me try running it. I'm going to run this command now, and you see that will tell me that I already have this. The requirements already satisfied. That I have SGBoost installed, or if it has the latest version, it will update to the latest version yet. So just take note of this. SGBoost is not part of sklearn. It is not part of sklearn package. You have to import it as a separate library. You understand? You have to import as a separate library. You can see here, I've installed it already, so it's telling me the requirement already was satisfied. So that is it for SGBoost. You can follow the same pattern with all other that we've looked at. So you can come and say SGB, and you say SGB classifier that you've imported. Enter. All right. So if you see the parameter, you see that basically nothing. Right. So you just put your SGB and say dot fit. It still follows the same process. Fit dot predict all of that, but the thing is different. It doesn't come in sklearn. So you see dot s train y train. So to run this, you see all of the parameters that we have here, right? So and then you can now use to make predictions, and then evaluate the model and all of that. So these are the different ensemble methods and ensemble algorithms that you will be using, the most common ones. Okay, so I think by now you are already familiar with how they work, what ensemble learning is, the different methods in ensemble learning, the different technique in aggregating or getting your final prediction, which is max voting, averaging, and weighted average. So as you can see here, we looked at all of that: ensemble learning types, parallel and sequential, ensemble techniques, mass voting, averaging, and weighted average. Then we looked at bagging, which is called bootstrap aggregation, and we looked at the type of bagging, which is random forest algorithm. This is the only example algorithm under bagging. All right, that we looked at. So we looked at how to use the code, how to import it, and all of that. So we also looked at boosting. So we have boosting, another method for ensemble learning. So we have different boosting algorithms. We have other boost, we have gradient boost, we have SGBoost. We have this other tool that we have here, like GBM and CatBoost. So you can as well look at them and just see how they differ. Okay. So we looked at also how the boosting algorithm works and how the bagging algorithm works as well, the advantages and disadvantages. And then we also looked at SG. So by now, you should now be comfortable with the different ML algorithms. Right? You might not necessarily be 100% comfortable, but at least you have an idea of what algorithm to go for when you want to build a machine learning model. Now you are making a lot of progress. You now have this knowledge in your toolbox. You now know the different kinds of algorithm and the ones to choose when you want to perform or build any ML model. So moving forward in the next class, we're now going to look how to improve your model. Or we'll first look at how to pre-process your data actually, because most of the data you're going to be using, they are not processed like the ones in sklearn. They'll be giving you raw data that you have to process so as to fit the fit the ML model that ML algorithms that you're using. Because if you pass in the wrong data format into your ML algorithm, it will give you error, right? And it's a very frustrating thing to see. So I'll show you how to pre-process your data so that you'll be you would have a seamless process in building your ML model. Okay, so we'll look at preprocessing of our data, and then we'll move on to looking at how we can handle different things like overfitting and all of those things that would make your model to perform poorly. So we're going to look at other things basically, right? So we've looked at the algorithm. Now we're going to look at how to make the model you are building with these algorithms better. All right, so that is it for today. We've actually come to the end of the class, and we've looked at a lot, right? We looked at quite some few things. So this is going to be the end of the different algorithms we are going to be looking in ML. So we've looked at logistic regression, linear regression, KNN, SVM, decision tree, random forest, SGBoost, gradient boost, and other boosts, right? So just keep all this at the back of your mind. Although we have another one which is called naive Bayes, right? So, but looking at that, but these ones that we've looked at, they're sufficient for you to do whatever it is you want to do. But if you want to extend, that is very, very fine. All right. So that is going to be it for this class. That I think we actually overshot a little, but that's fine. So please, I'll be taking question now, and then we call it a day. So if you have any question, please just indicate. Please. We need to round off as soon as possible. Yeah. So thank you very much. I'll be waiting for your questions. All right. Shamsuddin, you have a question? Please go ahead and speak. Your mic is on mute.
Good evening, sir.
Yeah. Good evening.
My own question is based on k-fold validation. Maybe instead of splitting our data into train and test, what if we use k-fold validation? Can we categorize it in category of ensemble method, since we do take the average at the end to be the lost, maybe taking the average of the lost or average of the accuracy to know exactly the performance of our machine learning. So can that one also be categorized as part of ensemble method?
I don't think I got your question exactly. What are you asking? Are you asking about k-fold or what?
In five-fold validation, since each and every model used to train in every iteration, maybe in every cycle. So after the training, the 5 model that you train under k-fold validation, for example, if we use 5-fold to train the model, after the training, then we take the average of the 5 weight of the model that have been trained during the process. But I now see from the explanation here, the process of 5-fold k-fold validation is in line with what you just explained. I said, can we also categorize it as an ensemble method?
Okay, I think I get your point. K-fold validation is basically just for evaluating your model, right? You can't actually consider it as an ensemble, because ensemble methods they have other things that are involved in getting the final prediction, right? So if you use k-fold and then you split your data and all of that, you just get different um um, accuracy based on the code you are using. But ensemble technique, as I've explained, they have other things that are involved in it. They have other things that are happening aside the aside what you just talked about now. For example, the random forest, it doesn't just split the data set into subsets. You also get random features for each of those subsets, right? For the other ones, the boosting algorithms, you've already seen, as I've explained, the process in which it uses to get the final prediction. So I understand what you're trying to ask. K-fold validation is a technique as well, that you can use to just evaluate your model performance. So you can use that separately when you are training on a single model, right? when you want to train maybe a decision tree, you can just use K4 to divide your model so as to assess how well your model is performing. But that is a different thing entirely. That is actually a separate thing and out of the scope of this class currently. But it is not the same thing as ensemble learning, if that is what you want to know.
All right, thank you, sir.
All right, Ozioma, please ask your question.
Okay, thank you so much, sir. My question is actually on bagging. Can you hear me, sir?
Yeah, I can hear you.
Okay, if I get you, you said in bagging, multiple models are trained independently on different random subsets of the training
Yeah.
data. So my question is, how do you decide the number of base model to use in bagging? Hello, sir.
Um, I thought we looked at that when we were looking at random forest. Random forest, it is using decision tree as the base model, right? And number of estimators by default is 100. That is 100 decision trees. So
100.
what will be happening is that your data set will be split into 100. You have 100 subset or 100 subset, yeah, 100 subset or bootstrap sample of that data set that will be trained on the 100 estimators that you already have. If you change it to 50, it will adapt it to become 50. All right, so
250.
that's basically what happens. So I hope that answers the question.
Yeah, yeah. Thank you, sir. We'll go through the video later. Thank you, sir.
All right, you're welcome. All right, I think in Nkechi Collins, you can unmute yourself. Yeah, you unmute yourself, Collins and Nkechi, please. I've unmuted you already. Oh, all right. Okay, so I think you might be having a network issue. So we're going to be wrapping up now. I think there's no other question. If you have your question, just drop it in the Q&A group. So that's going to be it for today's class. We've learned a lot. So please go over what we've done. Your assignment you'll be giving assignment this week. As I said, the assignment after next week, you'll not be getting assignment again. So you'll be getting assignment this week to evaluate yourself on what we've learned so far. All right. So please go over the videos, go over the materials, go over the textbook that I sent a while ago. Right. I don't know how many of us are still actually using that textbook as reference, but go over the ML textbook, go over your materials, go over a lot of other things. You can actually also look for materials online yourself, YouTube videos as well. So there are a lot of resources, useful resources out there that will help you understand better. So thank you very much for your time, for sticking up till this point. It is actually not easy to pay attention, especially to concept that is as technical as this. This is not something that most people enjoy, right? But for the fact that you are here shows your dedication and shows that yes, you actually want this. And I appreciate you and I actually applaud you for that. You are doing very, very well. So trust me, you be happy with yourself at the end of this program. You'll be happy with how far you've come and what you are able to achieve. So just stick with us till the end of this program, and definitely you will see a difference. So, as usual, please drop what you've learned in today's class, as there were a lot that were said. A lot were said in today's class. So please, a lot was said in today's class. So please drop what you learned from today's class. And that is going to be it. Thank you very much. Good night and have a fruitful week ahead.